Why do we need calculus? Let's find out. Let's start with something simple. What is area? At its core, area is about counting. How many unit squares fit inside a shape? Take this rectangle. We can literally count the unit squares inside, 1, 2, 3, all the way to 15. The formula, length times width, is just a shortcut for this counting. 5 columns, 3 rows, 15 squares total. A triangle is trickier, but watch this beautiful trick. Duplicate the triangle. Rotate it 180 degrees around the hypotenuse midpoint. The two triangles form a perfect rectangle. So one triangle is exactly half the rectangle, half of base times height. Even the circle has a hidden connection to rectangles. Cut the circle into wedges like slices of pizza. Rearrange them, alternating up and down. They interlock. They form a shape that's almost a rectangle. The width is half the circumference, pi r. The height is the radius r. Area equals pi r times r, which is pi r squared. Notice the pattern? We convert shapes into rectangles we understand. But then, the real world shows up. Here's the parabola, y equals x squared, one of the simplest curves in mathematics. What's the area of this shaded region? From x equals 0 to x equals 1. Can we count unit squares? The boundary is curved. Squares don't fit cleanly. Can we cut and rearrange? What would we even cut along? This shape doesn't decompose into anything we know. And this problem appears everywhere in disguise. Imagine you're driving. Your speedometer shows your velocity at each moment. If you drove at a constant 60 miles per hour for 2 hours, you'd travel 120 miles. Easy. Velocity times time. But what if your speed varies? You accelerate, slow down, stop at lights. The total distance you traveled is the area under this velocity curve. Same problem. What is the area under a curve? This appears in physics, economics, biology, engineering, everywhere. Here's where a beautiful idea comes in. We can't calculate this area exactly. The curve is too complicated. But what if we don't need exact? What if we start with an approximation? One rectangle? That's a terrible approximation. Way too rough. But it's something. It's a starting point. What if we use more rectangles? Watch what happens as we use more and more rectangles. 4 rectangles, pretty rough. 8 rectangles, better. 16, 32, 64, 128. Notice what's happening? With each step, we're getting closer to the true area. The gaps are shrinking, the excess is disappearing. Let's focus on a specific example. The area under y equals x squared from 0 to 1. With 4 rectangles, the sum is 0.468. With 10 rectangles, 0.385. With 100, 0.338. With 1,000, 0.3338. With 10,000, 0.33338. The numbers are converging to 1/3. As n approaches infinity, the sum approaches exactly 1/3. Now here's the profound question. What if we could use infinitely many, infinitely thin rectangles? Then the approximation isn't an approximation anymore. It becomes exact. This is the heart of calculus. This process, adding up infinitely many, infinitely small pieces, has a name. It's called integration, and it's one half of what we call calculus. This symbol, the integral sign, it's literally an elongated S for sum, because that's what we're doing, summing up infinitely many pieces. The dx represents the infinitely small width of each rectangle, and f of x is the height. Together, f of x times dx is the area of one tiny rectangle. So the area under y equals x squared from 0 to 1 is written like this. The integral from 0 to 1 of x squared dx equals 1/3. This single expression captures the entire infinite process we explored. 4 symbols, infinite meaning. But here's what's even more remarkable. This same idea, breaking complex things into infinite simple pieces, solves problems far beyond just area. Distance from changing velocity, integration. Work done by a varying force, integration. Probability, integration. Mass from density, integration. Electric charge from current, integration. The same elegant idea applied everywhere. Let's recap what we discovered. Area is fundamentally about counting. Curves break our simple formulas, but rectangles can approximate any shape. More rectangles give better approximations, and infinitely many rectangles give the exact answer. This is the power of calculus. It tames infinity. It makes the impossibly complicated become calculable. Every curved area, every varying quantity, every continuous change, all become accessible through this one idea. Break it into infinitely many, infinitely small pieces, and add them up. This is just the beginning.